What is the area of a sheet of aluminum foil that is 12.00 centimeters by 2 centimeters? In other words, what is 12.00 times 2? The area of this section of foil is 20 square centimeters. To understand this, you have to understand something about significant figures and precision. Measurements are important in science, but not all measurements are equal. Let's say you want to try to PR in the 100-meter freestyle. Your coach pulls out his watch and takes a look at the second hand as you jump in the water and swim across the pool. As you get out, he calls out your time, 52 seconds. That's not a very good measurement, coach. It'd be nice if there was a little more detail in that number. Now let's say that your coach times you with a stopwatch. Your time is 52.12 seconds. Which measurement is better? Which carries more meaning? Obviously, the number from the stopwatch has more detail. It's more precise. When we make measurements, we try to get as much detail from the measurements as possible. This is reflected in the number of digits in the measurement, specifically the number of significant digits. You see, sometimes some of the digits in a measurement don't carry any meaning. They're just placeholders. For example, the zeros in this first measurement are just here to place the decimal correctly. They don't add any precision to the measurement. And it's the same in the second number. These zeros help show the magnitude of the number, but they don't add any more detail to it. In this measurement, all the digits are significant. In this final number, the leading zeros are not significant, while the zero at the end does carry meaning. So you probably noticed, it's the zeros that are kind of confusing. How can we tell when zeros are significant or just there to place the decimal correctly? Well, when I learned about significant digits, I had to learn 5 rules for counting Sig Figs. But since then, I've learned a much easier technique. But this technique is going to require a little knowledge of geography. Okay, not much knowledge. You just need to know where the oceans are. In case you didn't know, that's the outline of the United States. And on the left side of the map, or the west coast, we have an ocean called the Pacific Ocean. On the east coast, or the right side, you have the Atlantic Ocean. Now, let me show you the Atlantic-Pacific method for counting significant digits in a number. First, to determine the Sig Figs, you must be counting digits from the correct side. You count from the Atlantic side if the decimal is absent, and you count from the Pacific side if the decimal is present. You get it? A is for absent or Atlantic, P is for present or Pacific. In the first number, the decimal is absent, and I'm counting this from the right. In the second number, there is a decimal present, so I count from the left. Next, begin counting digits with the first non-zero. So begin counting with 6 in this number, and begin counting with the 9 in this number. Finally, count all of the digits to the end, even the zeros. 1, 2, 3, 4, 5. So my first number has 5 significant figures. The second number has 1, 2, 3, 4. 4 significant figures. At this point, you should pause the video and write down these rules. To save time, you might choose to do a screen capture. Either way, you'll want these at your fingertips so that you can practice applying them to the next few examples. Let's try some examples. Use the Atlantic-Pacific rule to determine the number of Sig Figs in each of the following measurements. Pause the video while you do these on your own. Then play it back and check your answers. This first number has 2 significant digits, the 4 and the 1. The second number has 4 significant digits. The 0 at the end was not counted as significant. In the third measurement, we only look at the number and not the 10 to the 6th part. This number has a decimal present, so we count from the Pacific side, and get 3 significant digits. In the fourth measurement, there are 3 significant digits, the 7, the 2, and the 0 that follows. In the fifth measurement, there is no decimal, and it has 2 sig figs. The final measurement looks a lot like the previous one. However, when the decimal is present, this number will have 4 sig figs. Let's look at what happens with sig figs when you add or subtract several measurements. Say you want to add the masses for several objects measured with different balances. The first object is massed with a balance that reads 126.3 grams. A different balance is used for the next object and reads 8.308 grams. A third object has a mass of 21.07 grams. So the total mass is 155.678 grams, right? Now hold on. There's no information from the thousandths place in this last measurement, and we're missing data from the hundredths and thousandths place in this first measurement. So how can I honestly report the total mass to the thousandths? I can't, because the first mass only has precision to the tenths place. I must also round my answer to the tenths. So the answer is reported as 155.7 grams. In other words, when adding or subtracting measurements, you must round your answer to the decimal place of the least precise measurement. So how about sig figs when you're multiplying or dividing measurements? Let's say you want to calculate the mass of 14 milliliters of ethanol, which has a density of 0.806 grams per milliliter. And you know that multiplying these two measurements gives you the mass. 14 milliliters times 0.806 grams per milliliter gives us 11.284 grams. However, we can't keep all these digits. The rule for significant digits when multiplying or dividing says to round these answers to the number of sig figs found in the least precise measurement. There are 3 sig figs here, but only 2 in this measurement. So we have to round our answer to 2 significant digits and write 11 grams. It would be nice to have a more precise answer with more sig figs, but it wouldn't be honest, if you know what I mean. You see, I don't know this mass to the thousandths place because I didn't know the volume beyond 2 sig figs. So, back to the area of aluminum calculation. When we multiply the dimensions of this aluminum, 12.00 centimeters times 2 centimeters, we can't forget the precision of these two measurements. 12.00 centimeters has 4 significant digits, but 2 centimeters only has 1 sig fig, and thus it's a pretty lousy measurement. So this limits the precision of our answer to just 1 sig fig, and we round our answer off to 20 square centimeters. I hope this taught you something about sig figs and that you can apply these rules to your chemistry course.